Hey everybody, welcome back. In this lecture, we're going to talk about leg IK. This is one of the most interesting and awesome features of Unreal Engine because you get to make the legs look a lot more natural, especially on a slope. If you're stepping up on a ledge or perhaps a step or a steep slope, you can actually have the legs step up onto that slope, which is what the legs would naturally do. And this is becoming more standard in video games, especially since Unreal Engine has this feature built in to the default third-person mannequin in the third-person template project. So we should know how to do this from scratch. So we're going to make a control rig and implement this on our bow and arrow archer character in this video. So let's go ahead and get started. This video is made possible by the following patrons. Shout out to Stuart Jones, Sam Heifer, Doug Bell, Gregory Leck, 313 Ventures, Greg Beavers, Paul Berry, Richard Ostro, Elimination, Adam Eisen, Coop56 or Co-op56, Richard Stans, Lee Acavito, Ronald Guida, Kameen Avery, Andre, Tech Dwarf, Florian Blaine, Technicolor, Janan Rajartnam. Thank you all so much for the support. I really appreciate you guys. All right, so we have turning in place and everything's looking great, but we still have our legs up in the air when we're on a ledge or if we're on a slope. So that doesn't look really all that great. We're going to make a control rig to implement leg IK. Now, IK stands for inverse kinematics. And that is how we can move bones, specifically end bones, like the foot, and all the other bones attached to that leg bone or foot bone will move along with it in a natural manner. That's what Unreal Engine's full body IK system is capable of doing. Now, to do that, we need a control rig, and that's an asset we can create here in the editor. So here in our Archer folder, we have blueprints. I've moved my third-person character here into the Archer folder, but we can move that right into blueprints along with our other blueprints here. And now it's time to start organizing these folders a bit better because we have some different things here like the character and the arrow. So let's go ahead and make a new folder here. I'm going to call it character, and we're going to move the BP third-person character and the animation blueprint right there into character. And we have the arrow blueprint, so we're going to make a new folder called arrow and stick the arrow right there in the arrow folder. And the running blend space can go straight into character. And we have the crosshairs. We're going to make a new folder called HUD and stick the crosshairs widget blueprint into the HUD folder. So now we're a little more organized. And in the character folder, we have the BP third-person character, and the animation blueprint and the blend space, those can go into an animation folder, as those are animation related. So we'll go ahead and stick those there, and we're ready to make our control rig. Now, a control rig is animation related, but we're not going to put it in an animation folder. We're going to make a new folder called rigs and place it in there because rigs are kind of their own thing in Unreal Engine 5. So we're going to make our new control rig right here in rigs. So we're going to right click, go to animation and find control rig. And when we select control rig, we're asked for the parent class. We're going to select just control rig and click create. And we're going to call this CR_Archer, as this is the Archer control rig. Now we can double click this, and in the control rig editor, we have an event graph, sort of like a regular blueprint event graph, only we have this forward solve node. Now control rigs have a forward solve and a backward solve, and we can use all sorts of tricks in control rigs to move the bones of a given skeleton. Now for IK, we just need forward solve. Backward solve is when we can go back and perform further operations on things that we've moved or changed. But for leg IK, forward solve is enough. So we're going to make a control rig here and alter the feet so that they're always on the ground properly. So here's how we're going to do it. First, our control rig needs to know what skeleton we're working with, as skeletons have bones, and we're going to be changing the bones. And if we expand the left menu here, not only do we have My Blueprint, where we can see and add functions and variables, but we also have these other tabs, including Rig Hierarchy. And this is where we can import a hierarchy of bones. If we click Import Hierarchy, we can select a skeletal mesh, and we're going to select the skeletal mesh we're working with. Now, I can type Sparrow, and I'm using Sparrow Autumn Fire, so I'm going to select that and click OK. And as soon as I do, I now see Sparrow here in the viewport, along with all the bones in the skeleton. Now, if you're working with Sparrow or pretty much any Unreal Engine provided skeletal mesh, you're going to have the typical Unreal Engine mannequin hierarchy of bones. And that often includes IK bones. If we search for IK, we'll see that we have some IK bones. So let's talk about IK bones for a moment. In fact, I'd like to go back and find our skeleton asset. And I can easily find that by simply going to my character blueprint, opening that up, selecting the mesh, and browsing to that skeletal mesh here. And double-clicking to open that up, and we can see the skeleton here. And notice up by the root, we have these IK bones. Now, IK bones are special types of bones used for, well, IK, inverse kinematics. And here's why they're special. They're not skinned to the mesh in any way. What I mean by that is typical bones are skinned to the mesh itself, which means when the bone moves, the mesh moves along with it. If we find one of our bones, such as the calf, this is the right calf bone, I can rotate the bone and the mesh rotates along with it. It's skinned to the bone. But the IK bones are not like that. They're not skinned to anything. They're kind of like these invisible imaginary bones, and they don't affect the mesh at all. And the reason is because we can move these bones separately and then move the actual bones that are skinned to the mesh to follow those IK bones. So they're kind of like these handles that we can move around and then make the skeleton adhere to those transforms. Now, this is better than moving the actual bones themselves because we can move our IK bones to a particular target and we don't have to just snap the real bones to those locations and rotations. We can do things like smoothly interpolate towards those IK targets. So it makes things a lot more versatile for us. Now, there's an IK foot root bone, which is at the same location as the actual root bone. And if you weren't aware, the root bone itself is not actually skinned to the mesh either. It sort of acts like a reference point, like an origin for the skeleton. It's really its own bone, and it's the parent to all other bones. Well, if we have IK bones, they need a parent as well. So there's always an IK root bone, and our IK foot bones are parented to the root. They're children of the root. And notice, they go from the root up to the foot. So the IK foot L bone, for example, is simply a child of the IK root. And again, it's not skinned to anything on the mesh. If we move it, nothing moves. So we're going to take advantage of these IK bones in the control rig. So here's what we're going to do. We're going to go into our control rig, and we know that we have these IK bones. So we're going to be working with those. And the first thing we want to do is figure out where we should put the bones. Now, here in the viewport, we see that the legs look just fine, right? There's no problem with them, and that's because the problem arises when we're on a slope. That's when we really see the problem, because this back leg here should be on the ground, right? We want to move it down to the ground. And that means we need to move really the whole skeleton down. And to move the whole skeleton down, we'll move the pelvis down. That's because the pelvis is actually skinned to the mesh, unlike our root bone. If we go back into the skeletal mesh editor, we can find that pelvis. And if we move the pelvis, the whole body moves along with it. So it's kind of like the root bone. The root bone itself is the actual parent for the entire skeleton, but the pelvis is located up here on the hips, and moving that will also move everything without moving the root bone. So the root bone itself stays still and the pelvis moves, and the whole skeleton moves along with the pelvis. So what we're going to do is end up moving that pelvis down, but we also want to control the locations of the feet so they're exactly where they need to be. So in this case right here, my left leg should be up on the ledge. It's already in the the right spot. But the right leg should be down, which means the pelvis should be down. And when the pelvis moves down, we want the legs to bend. Okay, so we know our goal. That's what we want to do. And in order to do that, we'll need a way to know where to move those legs to. Because, we'll go back out here again, if the foot is up here, right, it's like 12 inches away from the ground. And the way we're going to figure out exactly where to move this foot is by doing a sphere trace. A sphere trace is basically drawing an imaginary sphere and pushing it down all the way down until it hits something. And once it hits something, we'll know the location of that hit. And we'll use that elevation, that Z value, that Z component of the location of that hit to know where our foot should go down to. Now, it could be our left foot, it could be our right foot. We don't know which one is going to need to go down. So we're going to have to do this sphere trace from both feet downward. And we'll find this delta, this change that we need to do to that foot. And here's what we're going to do. We're going to move our pelvis down by that much. That's our goal. And once we move our pelvis down by that much, so in order to do that in our control rig, we need a function that we can call to do this. So we're going to go to the My Blueprint tab here and make a function. So we're going to click Add, we're going to click Function, and this function can be called Foot Trace. So we'll have one function, we'll reuse it once for each foot. And this is where we're going to do a trace from the foot down to the floor, down to the ground. Now, if we're going to reuse this function once for each foot, we need an input parameter so that this function knows which foot we're tracing from. So what's the input parameter type going to be? Well, let's see. Right here under Inputs in the Details panel, we can click the plus icon to get a new input. And by default, it's called argument and its type is Boolean, but that's not the type we want. So let's click the drop down. And the type I'd like to use is called Rig Element Key. If we select that, we'll see that it's color-coded light blue. So this is the input type. And the reason I'm choosing this type is because this struct has two items in it. It has an enum called type and a name called name. So let's click the entry node again and rename this argument. And we're going to call this IK foot bone. So let's see what this type and name mean. What is this enum called type? Well, let's collapse this, and we're going to find out exactly what this type and name are by right-clicking and typing get transform, hitting enter, and we see that this type of node, get transform, requires a type and a name. Now, type, this enum, can take on any number of these values, anything from none to bone to even null to control, curve, or reference. Now, a bone is what it sounds like. It's a bone from our skeleton hierarchy. This includes IK bones. And we can get the transform of any bone in our skeleton by name. We can click the drop down and select one of these bones, like the thigh L, for example. But also notice get transform bone has an input called item. This is a rig element key, and we know that rig element keys contain a type and a name. So once we call this function, we can pass in a rig element key, and that will contain the bone and the name to use for this function. So all we need to do is plug that light blue output pin into get transform bone, and it'll get the type and name information from that input. And get transform bone can be in global space or it can be in local space for that bone. We're going to work in global space for this video, and we're going to do a sphere trace using the bone transform as reference. Now, we're going to do this, as I mentioned, from the left bone and the right bone. So we're going to call this function twice. Now, let's just imagine we're calling this and passing in information for the left foot bone for a second. We want to do a sphere trace, and we want to do it straight down to the ground. Now, this foot might be already on the ground, so we're actually going to do the sphere trace from just above the foot. And we're also going to push that start location for that trace over a little bit so we don't hit the foot. So we need to do a little bit of math here. Now, get transform bone returns a transform, but most of these control rig input and outputs have little drop downs that let us expand these types because they often are composed of other types. A transform is composed of a rotation, translation, and a scale, just like the item is composed of a name and a type. Now, we're going to take the location, which is called translation, same thing, and we're going to add to it so that we can get the location of the foot, but just raised a little bit and off to the side a little bit. So let's get this translation, which itself has a drop-down we can expand to see the X, Y, and Z. Now, this is the transform of the bone corresponding to that information in the rig element key that we're going to pass in once we finally do call this function. So this transform location is the location of that foot bone. Okay, so what we're going to do is take that foot bone, we're going to take that location and add some values so that we get the location raised a bit and moved a bit. So let's right click and type add, and we want to add vectors. So let's find an add vector node. And just like the other vector inputs and outputs in control rigs, we can expand A and B. So this add will add two vectors together. And if we add a vector pointing straight up by, let's say, 50 units, so we can put 50 in the Z here for the B vector, then that will take that location and move it up by 50 units. That's what we're going to do here. So we want to do that, but we also want to move over in the Y by about 5 units or so. So I'm going to take the Y and add, and this time get an add float, and add 5 to the Y. And we can use the X straight in as the X for the A vector. We can use this new Y for the A vector. And for the Z, we're just going to use our foot bone Z, because basically what we're doing here is getting our foot, moving it over by 5, and then adding this vector B, which will move it up by 50. That'll be the start for our sphere trace. Now we also need an endpoint for our sphere trace, and we're going to do something similar here, only I'd like to add a vector pointing down by about 100 units. So that way we'll trace from 50 units above the foot down to 100 units below the foot. So instead of an add for the endpoint, we're going to use subtract. We need a subtract vector node. So we can go ahead and expand A and B here, and our point here is going to be the same thing we plugged into the add. So we got to plug X from our get transform straight into A's X. We're going to get this add node and use that for the Y, and we're going to use Z for the Z, just like we plugged into add. So we're using the same vector, only this time we're subtracting the vector, and the vector I'd like to subtract is 0, 0, 100. So when you subtract a vector, that results in taking a location and pushing it downward by 100 units. That's what this node is doing for us. Now, this gives us a start location and an end location for our trace. Let's comment these. We'll comment the add. We'll hit C for a comment and say start, and we'll comment the subtract and we'll say end. Now we have a start and an end, and now we need to do the actual sphere trace. To do that, we're going to right click and type sphere trace, and we're going to sphere trace by trace channel. That gives us this node, which requires a start location and an end location and a radius. We can choose about 3 for the radius. This doesn't need to be a large sphere. It can be pretty small. We're going to plug in the result of the add to start and the result of the subtract to end. So what this is going to do is do a sphere trace from 50 units above the foot to 100 units below the foot. And the result of this is that we'll have a hit location as long as we got a hit. And that hit location is what we're interested in. That's the only reason we need this function. That's going to be our output. So we're going to take our other node. Here it is. It's called return. We're going to select that, and in the details panel, we'll add an output for this function. So we'll click plus next to outputs, and this will be a vector. And the vector we can simply call hit location. So this is the hit location from our trace. And we'll take our hit location from the trace, plug it into the return node, and now we have a nice little function that will do a sphere trace for us. And it's going to take the rig element key for whichever bone we choose and trace, so we can get that trace result. Now we need to call this function. So we're going to go back into the rig graph to call it. Now, before we do a trace, I'd like to do a branch. Let's hold B and click to get a branch. And our condition for this branch will be a Boolean value, and once we use this control rig, we'll be able to pass actual values into our control rig. And I'd like to make a Boolean here for whether or not we should even do the trace, because there will be situations where we don't need to trace, such as when we're falling. So let's go to the My Blueprint panel, click Add, and we'll add a variable. And it's already a Boolean by default. And I'm going to call this should do IK trace. So for whatever reason, if this Boolean is ever false, then we won't even do the trace. And take a look at what Booleans look like in the event graph. They're a little different than they look like in regular Blueprint graphs. But make no mistake, this is just a Boolean get node. So now we need to actually call our new foot trace function. So we're going to click on it, drag it on out, and we're going to call it. Now notice it has the input IK foot bone. It's a rig element key, and we can expand that drop down and we can choose values. We can hard code values right in. Now I'd like to choose our IK bone, the left one for this one, and select that for the name. So the type is going to be bone. So let's open that drop down and select bone, and then open the drop down for name and find that IK foot bone, and it's called IK foot L. So once we call this function foot trace, we'll have a hit location. And really the only thing we care about from this hit location is the Z value. We just care about the elevation. How far off the ground is our foot, right? So we can expand this drop down and take the Z from this hit location and promote it to a variable. And I'd like to rename this new float variable, and we're going to call this Z offset underscore L underscore target. So this float value is going to be a target to use to try to move our foot. Now, we have this for the left foot, but we want to do this for both feet. So we're going to call foot trace again. I'm just going to select it and Control D to duplicate it and change this from IK foot L to IK foot R. And I'm going to take the Z from this hit location, promote it to a variable, and rename this one to Z offset underscore R underscore target, and connect that. So now I have these targets, and we're going to use these when we move our feet down. But we also need a target for our pelvis. Remember, we want to move the pelvis down also. And we want to move the pelvis down by the same amount that we're moving the foot that's the highest from the ground. And just to picture this, if I go up to a ledge here, notice that the leg here to the right doesn't really need to move down. It's the leg here to the left that needs to move down. And this amount that we're moving that leg down by, that's how much we're going to move our pelvis down by. So we need to find out which of these two results from our sphere trace is the lowest in the Z direction. That's the next thing we need to do. So we can comment this first thing we did here, and we can say step 1, sphere trace from feet. That's step 1. And because we're going to be doing multiple things here, we're going to have a sequence node. And I'm going to have the sequence node right out of forward solve. So let's drag out, do a sequence. And here in the control rig, the sequence has A, B, C, and D. So A will be the first step. Step 1, sphere trace from feet, as long as that Boolean is true. So that's great. Now, we have these Z offset targets, and those are going to be where we're moving our feet towards. But as I mentioned, we can smoothly interpolate our feet towards the targets. So we're going to have another pair of variables called Z offset L and Z offset R. And these are going to be smoothly interpolating toward these target values. So let's make 2 more floats. The first one will be Z offset underscore L, and that's going to be a float. And the next will be Z offset underscore R, and that's going to be a float. And we're going to take those values and interpolate them towards our Z offset L and R targets. That's the next thing we're going to do. So let's get first our Z offset L target. We'll get that, drag off of it, and to interpolate, we're going to use alpha interpolate float. Now, alpha interpolate float takes a value, that's going to be the target value, and the result of this is going to be some value that smoothly gets close to our target value. And that's what we're going to use to set our Z offset L. So we're going to set Z offset L using the result from alpha interpolate. And we have interp speed increasing and decreasing. These determine how quickly our Z offset L will approach the target value. We'll set these to 15 and 15, and we'll see how that looks. And alpha interpolate has a checkbox for interp result. We want that to be checked because we want a smooth interpolation. Now, scale will affect this, but we want the alpha interpolate to be fully effective, so we're going to leave the scale at 1, and we can leave all the rest of these inputs at their defaults. We're going to connect this to our B output from the sequence, so that'll be the second thing we're doing. So we're doing this for the left foot target. We want to do this for the right foot target. So we're going to get our Z offset R target, get that, drag off and do an alpha interpolate for this one. So alpha interpolate float, we want to change interp speed increasing and decreasing both to 15 and check interp result and use the result of this to set our Z offset R and hook those up. And now what we're doing here is we're making our Z offset L and R smoothly approach our Z offset L and R target values. Those are what we got from our sphere trace. Now I mentioned we're going to want to move the pelvis down as well. So we're going to want a Z offset pelvis variable. So let's add a float variable called Z offset underscore pelvis. And we don't need to interpolate this because we're going to set it to one of these two. And the one we choose is going to be the one that's the lowest in the Z direction. So we need to quickly calculate which one of these is lowest. And we can do that by getting Z offset L and Z offset R. We'll get both of those, drag off of one of them and type less. And we'll get a less float node, which takes two floats and returns true if A is less than B and false otherwise. And we can take Z offset L and R and duplicate them here and drag off of one of these and type if. And we can get an if node, which will take both of these float values and a Boolean. We're going to plug in the result from less. And if will return a float. It'll return Z offset L if the Boolean is true and Z offset R if the Boolean is false. So the combination of these means that if Z offset L is less than Z offset R, that's what we'll get from our result. But if Z offset L is not less than Z offset R, that means Z offset R is lower, and that's the value we'll get from here. So this gives us the lesser of the two, and that's what we're going to set our Z offset pelvis to. So we'll get a setter for that and plug in the result, and now Z offset pelvis will be equal to either Z offset L or R, whichever one is lowest. And that's going to be what we do for our step 2. In fact, we'll just call these steps 2 and 3. We'll say these two here are interpolating, so we'll comment these and say step 2, interpolate Z offsets toward their targets, parentheses, from the sphere trace. So that's step 2, interpolate Z offsets toward their targets. The targets are from the sphere trace. That's step 2. And then step 3 is to find out which one is lower and set that for Z offset pelvis. So we'll comment this and say step 3, set Z offset pelvis to the lower of the two. We'll just say that. So that's step 3. Okay, great. Now we have these target values. We're going to use these to modify the transforms of our IK bones. Here's how we're going to do it. Down here, we're going to right-click and type Modify Transforms. Now, Modify Transforms takes an input, which is an array of items to modify. But by default, it already has a single array element called 0. We can expand that. And here's what each of these elements in the array are. They're these structs that contain a type and a name. Now, we're going to want the type to be bone, and we'd like to modify the transforms of our IK bones using those values we calculated. So the first one we're going to choose is IK foot L. We're going to modify the transform of our left IK bone. So I'm going to hook up this execute with our C output from the sequence. This will be the third thing we do. I mean, really, it's the fourth thing we do if we consider this to be 2 steps. So we're taking our IK foot L bone. Now this modify transforms requires a transform, and we can choose how this modify transforms node will transform that IK bone. We can use additive local, so whatever the values in this transform that we pass in, they'll be added to that bone in local space. But remember, we're working in global space, right? These are all global coordinates, so we're going to choose from the dropdown additive global. Optionally, there are override local and global as well, which would take our transform and completely override the transform of the bone. We don't want to do that. We just want to add to the bone. So we're going to use additive global. And we don't want to add the entire transform. We just want to add to the translation. In fact, we don't even want to add to the whole translation. We want to add to the Z of the translation. That's the value that we stored up here when we calculated our Z offset. So we're going to use our Z offset L here for the Z. So let's get Z offset L and plug it into the Z right here. And modify transforms will take our IK foot L bone and add our Z offset L to it, which means we'll be moving that foot down to the ground, depending on the value of Z offset L. So that's how it works. And we're going to do the same thing for our right IK foot bone. So let's take our modified transforms, Control D to copy that. And for this one, we're going to choose IK foot R. This will be the right IK bone. And for this one, we just want to change the Z. We want additive global. And we're going to use Z offset R and plug that straight in to the Z for the transforms translation. So essentially, we're not moving the feet yet. The mesh itself will not change as a result of these because we're changing the IK bones. And remember, the IK bones are not skinned to the mesh. They're sort of their own thing, right? So we're moving the IK foot bones down. That's what this is doing. We're going to move the actual bones later, but for now we're moving those down. Okay, so that's going to be the next step. But we also want to move the pelvis down. So we're going to use another modified transforms. I'm going to copy that again, and this time we're going to choose for the name the pelvis bone. Now notice the difference here. These first two are moving the IK bones, but this third one is moving the actual pelvis. This means we're going to be moving the entire mesh down. So this one does move a real bone down. These two are IK bones. This one is a real bone, the pelvis bone. And we're going to use our Z offset pelvis for the Z. And again, it's additive global. So that's how that works. So this is going to be the next step. We can comment this, and this will be step 4, I believe. Step 4, we're going to say modify the IK bones and move the pelvis down. So that is our step 4. And we're almost done. We just have one last step to go, and that's to actually move the feet to the correct positions and use IK so that once we move the feet, the legs bend appropriately. So to do that, we want to use a node called Full Body IK. This is a shiny new feature in Unreal Engine 5, and let me tell you, it works pretty amazing. What it does is it takes a list of effectors. When we say effector, we're talking about some end bone, right, like a foot bone, and we're moving that bone, so moving the foot up or down, and the bones that are attached to that foot will move in the correct way. There are lots of math equations being solved under the hood here for us. This is quite a sophisticated thing the Unreal Engine is doing for us. It's really something we should appreciate. So Full Body IK takes an array of effectors. That means we can have multiple end bones to move. So we're going to click plus here to add an element to the effectors array, and we're going to choose one. Now before we do that, notice there's a root. We need to choose a root for the IK. Now, we're not going to choose the root bone, we're going to choose the pelvis because the pelvis is the first bone that's actually on the mesh that all the other bones move along with. So we're going to choose that pelvis bone for the root for Full Body IK. And our first effector can be our actual foot L bone. So we're going to get foot L, not the IK bone this time. This is the first time in our control rig where we're actually changing our foot bone. That's the bone that is skinned to the mesh. If the foot bone moves, the mesh moves with it, right? So let's connect this execute pin to our sequence. That's going to be our fourth and final thing. Now notice, as soon as I connect it, our pose changes. That's because our control rig is constantly updating even when the game isn't even running yet. And what we're doing here for full body IK is we chose our foot L bone, and this has an input for the transform. So it's asking us what is the transform that foot should be at. That's why we were changing these IK bones, because the IK bones have the transforms that we want our real bones to follow. We're going to use the IK foot L bone and get its transform. So we're going to right click here in the graph, type get transform, and we have a get transform bone node, and the type can be bone, and the name is going to be IK foot L. We're getting the IK foot L transform, and we're going to plug that straight into the transform input here. Now, it still looks funny, and that's because our full body IK has a settings dropdown. If we open that, we have root behavior, and by default, it's set to pre-pull, which says translates the root and all children by the average motion of the stretched effectors to help achieve faster convergence when reaching far. But we don't want that. We want to use pin to input, which locks the translation and rotation of the root bone. So notice, our root bone here doesn't look like its translation and rotation are locked, but we do want it locked. We want to move our effector, that's our foot, without affecting the root bone for the full body IK, which is the pelvis. So we're going to change this from pre-pull to pin to input. And now our pelvis is correct. It's locked. All right, so this takes care of our left foot. But effectors is an array, which means we can choose multiple bones to change. We're going to click plus here, and now not only do we have element 0, that's changing our foot bone transform, now we have element 1, and this can change another bone. We're going to find our right foot, so foot R this time. And for foot R, we want to use the transform of the right IK bone. So we're going to get transform, and for this node, for the name, we're going to search for IK and choose IK foot R. And we're going to plug that in to the transform to element 1. And now full body IK is going to take the transform for these IK bones and use that for the transform for the actual foot bones. And when it does that, it moves the other bones to where they should be. It'll bend the knees in the proper way. And that's going to be our fifth and final step. So let's comment this, and we'll say step 5, use full body IK to move the feet to the IK bone transforms. And now we have a control rig that will do leg IK for us using full body IK nodes specifying the left and right feet. This is great. So now that we have this control rig, how do we use it? Well, we use it in our animation blueprint. We'll go back to our anim graph. Now, in our anim graph, just before the output pose, we're rotating the root bone, right? Well, right after we rotate the root bone, we can use our control rig. We're going to right-click, type control rig, select that, and we'll have a control rig node. And if we select the control rig, we can scroll all the way down to control rig class, open that dropdown, and choose our control rig, CR Archer. We're going to select that, and now we have that set for this control rig. Now remember, CR Archer has a Boolean variable, and we're checking that before we actually do any trace. Before we call foot trace, we only call the foot trace function if should do IK trace is true. Well, what about if it's false? Well, if it's false, then our Z offset variables, there's no need to have any value for them. We can zero them out. So we're going to get Z offset L and set that to 0 in the false case. And Z offset R, will set that to 0 in the false case as well. And our Boolean should do IK trace, we can set that from the animation blueprint. All we have to do is click the eye icon to make it visible and compile our control rig. And back in our animation blueprint, with our control rig node selected, we'll go ahead and compile the animation blueprint. And now we'll see should do IK trace. We can check this checkbox that says use pin. And now we have the ability to plug in a Boolean value here. So now we can control whether or not our control rig will do that foot trace. And we don't want to do the foot trace if we're falling. So let's get is falling. We'll use a not Boolean here and plug that straight into our control rig. So if we're ever in the air, we will not do that foot trace, and those offset targets will be 0. Now all we need to do is run our pose through the control rig like this, and our control rig will be working on our character now. Let's compile, let's save, and press play. And now we can run up to a ledge and we see our IK working. And this is beautiful. Now the cool thing about this is even as we're stepping and turning, our legs are adjusting and we're interpolating, right? So these are not snapping. We're not raising up in a rapid manner. We're smoothly raising and lowering that pelvis and those foot bones. So this is really looking nice. It really looks amazing and natural. And whenever we're on a slope, it looks like it should. Now again, that back leg is raised up above the ground a bit, and that's because of our idle animation. This is really the idle aiming animation. So when they made these animations, they made it so that when she's aiming, she's kind of on one foot. It's sort of on the tiptoe a bit, and that's intentional. And again, if we go back to our idle state and we replace that with a different idle animation like the bow down mode, then now we see that leg is on the floor, and that's more of a natural state. She's not aiming. I mean, of course, she's aiming while we're turning in place, but it looks more like it should look. So that's just because of the idle animation, and there are ways to edit animations. I show how to do that in my other tutorials. I'm not going to get into that in this video. In this video, we have now achieved IK, and this looks great. So now we know how control rigs work, we know how to do leg IK, and this is a really nice touch for games. It's something that's a really subtle difference, but it really does give that extra degree of realism, and games that implement this really give you a bit more immersion. Our animations are more dynamic, more procedural, and that's where control rigs can really shine in Unreal Engine. So I hope you enjoyed this video. If you did, please like, subscribe, hit the bell icon, and leave a comment below and tell me what you'd like to see in the next bow and arrow tutorial video, as there are still lots of cool, interesting things we can do with this. And if you want to get access to these videos a day ahead of time, join my Patreon. There'll be a link in the description below, and you'll have access to my brand new Unreal Engine C++, the Ultimate Game Developer course. This course is in a completely different universe than the Unreal Engine 4 version. We're doing an open world RPG style project. It's already looking amazing, realistic, and lifelike. So for early access to that course, you can join my Patreon and start taking the course early before the Udemy students will even get to see it. So become a patron. I really appreciate the support. It helps me to make these videos and continue doing this. So thank you very much, everybody. I hope you enjoyed this video. Stay tuned for the next bow and arrow tutorial series video. I'll see you soon.